Okay, so a quantum computer is nothing else than a many-body system which evolves under kind of special non-equilibrium conditions. Okay, so it's a bunch of qubits that will start from a given state, and the idea is that by applying certain gates or some unitary evolution, it will finally reach a state, another quantum state in Hilbert space, which is the solution of the problem we want to solve. So over the last say 2 decades, people realized that a quantum computer in this idea of many-body controlled many-body open system could fruitfully lead to some additional tools that were originally developed to understand quantum information protocols when applied to condensed matter or statistical mechanics system. So the idea of my 3 talks would just be to give a kind of very broad overview of how this quantum information techniques, tools, or whatever, which were initially thought to be applied to study quantum information processing, turn out to be very useful in a much broader context. So I'll try to just to give kind of a panorama. Of course, I had to choose topics, and yeah, this is essentially okay. It got stuck. Sorry. What happened? So what I'm supposed to do then? Okay. Okay. So I organized my 3 lectures in the following. But of course, if there is, I'm not able to change it. So okay. So let me tell you what is so essentially the content. So I will mostly talk about, I essentially talk about lattice systems. So we consider system in which I mean, I have a lattice of interacting particles. This can be an optical lattice or a spin array. So in the discussion I'm going to present, it's not really important to focus on the detail what I'm going to consider. And so let me start with further motivations for what I'm going to tell you. So in a very simple-minded way, I mean, people in StatMech characterize phases of matter, but just looking at local observables, correlations. Of course, this is not the end of the story. We know this, but let's say, roughly speaking, if you want to describe how a spin system will organize itself below the Curie temperature, then you just look at the average magnetization or how correlation decays and so on and so forth. And of course, if you go, if you want to go further, to understand how time correlations will evolve, you have to look also at Green's functions or time-dependent correlators. As long as you are, so you can look at, for instance, linear response. In this case, what you need to compute is the retard Green's function. And in equilibrium, essentially, it is enough to know one of these correlation functions because of fluctuation dissipation theorem. And that's it. If you go out equilibrium, then in addition to linear response, you are interested in computing also correlation functions. So this was, let me say, kind of the traditional approach to understand the physics of many body systems. Now, actually, there is much more than this. That are informations which are contained in the wave function that are not necessarily transparent by just looking at this correlation function. Of course, I mean, so in principle, if you compute all possible average between correlators, then you can extract this information, but probably these tools that I'm going to describe are much more efficient in extracting this information from the system. Moreover, if you look at, for instance, this type of correlations, then it is more complicated to discriminate between correlations between spins, say, that are classical in nature, or they really are quantum or entanglement between particles. If you really want to understand quantum correlations between, for instance, two spin in this lattice, then probably to do something more than just looking at spin-spin correlation function. So this is roughly the motivation. Let me summarize what is the plan of what I would like to present. So as I said, in the last 2 decades, quantum information tools led to new ways to understand many body systems, and I will try to motivate this. In particular, I will talk about entanglement and show you how entanglement behaves in several different situations. Example, I chose the good one that might interest you. Now, understanding entanglement, and I will define what entanglement is in the next slides, is important to grasp some features of quantum state, but it turned out to be important also to understand when approximations or numerical methods to simulate many body systems might be efficient or not. I will not talk about this in my in these talks, but there is a whole field related to simulating classical system using tensor network, which essentially relies on the knowledge that of how entanglement is present in the quantum system we would like to simulate. There are cases, and this I think I will discuss in the third talk. There are cases in which actually critical phenomena exist that are not visible in any of average observables. Like you just compute the magnetization, you see nothing, but they appear in some more complex quantum correlators. And I will present some example of this. Furthermore, why do we want to study entanglement? Because this may be, it is relevant to understand phenomena, several different phenomena, for example, thermalizations. And finally, quantum information tools may be relevant in, or they offer ways to detect singular behavior in some cases, and actually this is one of the examples I'm going to present, in some cases in which it is difficult to find out what are possible order parameters. So in all these lectures, I will talk about mostly about entanglement. There is an interesting topic that I'm not going to touch, is about the relation between entanglement and non-locality. And actually there is a whole discussion on how to understand when non-locality appears in many body systems, but this will not, I will not discuss. So what is entanglement? So if you have a composite quantum system, if it cannot be written as a product, let's consider first pure states. Okay, if the state cannot be written as a product of phi 1, phi n, then the state is entangled. This is for pure state. If I have to consider mixed state, then the definition is slightly different, because I can have an arbitrary superposition of classically correlated system. So if I have a mixed state, then I have to consider a density matrix, and if a generic superposition, superposition of tensor product of density matrices is still maybe correlated or highly correlated states, but it is not entangled. Okay, so this is essentially, whenever you have this situation, then you have an entangled state. And this large Hilbert space we are going to consider, I will have separable states, so those states which are of this form, and there will be the rest. And the question is now how to characterize, to find out what is in this rest here. Now, from what is implicit in this definition, that in order to define entanglement between parties, I have to define entanglement between this and that. So I have to define a given partition. Okay, so for instance, a simple case is just to consider this is the full system, and I just divide into regions A and B, and then I can ask questions. What is the entanglement between the region A and the region B? But of course, as you see, that if I have an n particle system, then this is this is not necessarily the only possibility. I can ask myself to check if a given state is entangled. This is already. However, much more important is also to quantify entanglement. Quantifying entanglement is important because in general, in quantum information protocols, entanglement is a resource to perform certain tasks that can be possible otherwise. In general, quantifying entanglement in many body systems is important because it will tell us features of the phases itself. So let me start from the simplest case, that is bipartite entanglement. Already at this level, you may imagine many different ways to ask the questions. So what is the entanglement, bipartite entanglement content in the system? And depending on the question you are asking, then you may get different information. So for instance, if you have a lattice, then you can ask yourself, what is the entanglement between these two sites? Okay. So this means that you trace out all the rest of the system, this n-2 sites, and then the question is that you would like to know what is the quantum correlations that these two sites share, their state being a mixed state. Now, I would like to stress that here I can define what is the correlations of spins. Just imagine like spins. I can ask myself what is the correlations between the spins in these two positions, and I can ask what is the entanglement shared by the two spins. And these two questions are completely different questions, and as I will show you in a minute. But in the same way, I mean, you can look at very different partition on region A and B. So don't ask between two sites, but just divide it in pieces into regions, your system, and try to understand what is the entanglement between these two different regions. In this case, it will become important to understand how the entanglement will scale with the sides and of the two systems. Now, so which is the best? There is no best choice, of course. I mean, essentially, part of the problem, and this to try to understand what you want to describe by choosing what is the good partition that will provide useful information. And we will see several of these examples, and in various examples we will see what we can learn. Of course, I mean, bipartition is not only the only choice. Let me start with a very simple case of 3 qubits. Okay, this just so you have three spins and just generically described by a density matrix. Of course, we have separable states. So the density matrix is just described by the product of ρ1, ρ2, ρ3, superposed with some probability p alpha. You may have entanglement because two of the spins are entangled and the third one is separable. And depending on what pair is entanglement, you have three combinations. You may have the case in which the three spins are entangled. And in particular case of these three qubits, then there are two different classes. These are just two examples belonging to these classes. So there are these W states. Just consider it's like kind of 1, 0, 0, 0, 1, 0 plus 0, 0, 1, or you can have this GHZ state, which have different forms. Now, just, I mean, so it is not possible to just to convert states belonging to this class to the other one by just doing local unitary operation. And just notice something. I mean, these are really genuinely tripartite entanglement states. And if, for instance, you trace out one of the three spins, the behavior of the reduced state of the residual pair is totally different in the two classes. For instance, if you trace out one, for instance, the third spin in the GHCZ, then you get an identity. It's totally mixed states of the 1-2 pair, while for the W states, you trace out the third spin and then you end up with a Bell pair. So this might tell you what is, I mean, kind of the fact that this belongs to two different nature of tripartite entangled states. Now, of course, I mean, this is just a simple example with three spins. So now if we go to a many body states, then you can imagine that I mean, the number of very different partitions proliferates enormously. And trying to understand the generic multipartite entanglement in an n-bit system is a complicated problem in itself. So I will not attempt to discuss this because I have no idea. So this is primarily because of my ignorance. So I will not attempt to say anything about this point. What I'm going to aim in this presentation is just to choose specific partitions of the system, trying to show that by looking at entanglement between this partition is useful to characterize the state. So therefore, I will not try to classify entanglement in the multipartite case, but I will just give example on how it behaves in a multipartite situation. So just a summary of what I'm going to discuss. So I will focus essentially most of the time on Hamiltonian system. I will discuss few cases of circuits, but mostly I will consider system that evolves with some given Hamiltonian. I will start first by considering ground states of these Hamiltonians and see how entanglement behaves. Afterwards means depending on how long it takes, maybe later today or tomorrow, I will discuss about how entanglement evolves in time, and the typical situation that I'm going to consider is just to that of a quench, quantum quench. So I will start with a low entangled or severable state, apply some unitary evolution due to some entangling Hamiltonian, and see what happens after some time. Then the last part, I will relax the fact that there is only an Hamiltonian, so the evolution is unitary, and I will consider cases in which the system, the quantum system is open, or maybe open because of losses, decoherence, whatever, but also because we do measurements or other sorts of non-unitary evolution. And I will discuss that peculiar critical behavior that will emerge in these cases. And I mean, all this story, I will try to present by just looking at various properties of quantum correlations. So I will start then with the ground state entanglement. Okay, so there is a plethora of Hamiltonians that I'm going to consider. This is to give you an idea. Most of the examples, I mean, are taken just using those Hamiltonians. So I will start with the simplest, which is one-dimensional Ising models in a transverse field. It's very simple, yet you can do a lot. I mean, people love it because you can do easy calculations. By Jordan and Wigner, you have essentially, this is an Hamiltonian of 3 fermions. The ground state is non-trivial, showing at the ratio, at the critical ratio of the exchange to the transverse fields, a transition between a paramagnetic and a ferromagnetic coupling. The transition is second order with some diverging correlation lengths. This is, of course, the simplest example. Then if we add additional ZZ interaction, then this 3 fermions will become interacting, so additional features appear. If a longitudinal fields, then this will add yet another qualitative features. The model is not integrable anymore, and eventually the various coupling can be disordered, and so MBL will become the dominant behavior, so on and so forth. So while most of what I'm going to say for the ground state is essentially will be based on the fact that correlation length in the system diverges of nodes. This additional ingredient that is having non-integrability of localization will play a dominant role in looking at the dynamics of the entanglement. So, so this part of the story will pop up later in this presentation. So let me start with yes. Sorry. And this one. So So if you have this only, so you have x interaction plus z, so a transfer speed by doing Jordan-Wigner transformation. So you can by expressing the spin operators with the fermions, then the Hamiltonian will become quadratic in the fermion variables, which is not the case if you. Yes, you're right. This is wrong. So this should be sigma x. Okay, sorry. I managed to change only the hx. Okay, sorry. This was a nice way to say that I was wrong, but okay. So let me start with kind of not talking about entanglement, but just one example how so of this quantum information tools. This is an idea that so essentially it was put forward by Zanardi in 2006, 2007. We just tried to look at the fidelity in the ground states, showing that this fidelity is an excellent way to detect transition. So essentially what you want to know is that you take your many-body ground state at a given value of the coupling lambda, and you just look at the overlap when you shift by some slight, take slightly different value of the coupling to lambda plus delta lambda. So what they showed is that the fidelity is very sensitive to the presence of a critical point. Actually, what they show is that it turns out to be much more convenient rather than looking at the fidelity, just at the second derivative, which is something which is called fidelity susceptibility. And but just showing, just taking the susceptibility, sorry, they show that this quantity is very sensitive to the presence of transition. And the idea is very simple. I mean, a phase transition is something dramatic that occurs in the structure of the wave function. So when you are very close to a transition, you change a little bit the conditions governing the system, and the change in the overlap is dramatic. There are also other aspects which are interesting by itself, but I will not say that is the connection to the Loschmidt echo, and also to the fact that this is susceptibility is related to the quantum geometric tensor which enters in the adiabatic evolution of states. An example of this is a paper by the group of Troyer that computed that this fidelity susceptibility in the case of Bose-Hubbard model, and then you see that there is a divergence. Okay, so actually what was nice in this paper is that they proved that they show that actually it's very efficient to compute by Monte Carlo, quantum Monte Carlo. Now, why it is interesting and why I wanted to mention this? Because so essentially, this is a quantity which does not rely on any understanding of what we have in the kind of order that we are looking for. So, I mean, essentially, if you are looking for certain type of orders, of course, you know what are the critical correlation function to study, but if you are kind of blind and you have no idea of what are the properties of the system you are studying, then this is a kind of very sensitive tools to really find out what are the singular region in the system. Yes. Yes. If I manage to go back. Just a second. I'll yeah. No, but I should be more able to. I'm stuck. Okay. So yes, sorry. So so suppose that you have so you can relate essentially this quantity to the fact that so if you have a spin particle, a spin coupled to, and you take the many body Hamiltonian as a bath, okay, then you can study what is the decays of the off-diagonal components. So you consider purely the phasing model, okay? So the system, the density matrix in the sigma basis, say, is unaffected in the population. So the population are not touched. So the only thing which happens are the off-diagonal components that do decay. And these off-diagonal components will decay, say, with some exponential type law, whose rate is related to the fidelity susceptibility. So depending on the correlation in the bath, you can detect by just looking how a single spin loses coherence. So there is no connection. So this was the, I want to give an example. Sorry, there is no connection there. I will come to entangle in the next slides. The only thing I wanted to show is that by just looking at properties of the wave functions, you can get, so I can try to find connections, but it's just, in practice, in this fidelity susceptibility, it's the entanglement of this probe with the rest of the chain, but you are perfectly right, okay? Okay, so now I'm going to talk about the entanglement. And I will show different cases. So the first one, which I will consider, is, so I think I started at 11:30, right? Okay. So I will first consider this two sides entanglement. Okay. Why I'm showing this? Essentially, the thing that I will show is that entanglement between two spins is not the same correlation between two spins. Okay. If you want to know the entanglement which is shared between these two spins, you have to determine the entanglement between a state, between two parties of a state which is mixed. So it is not easy, but this problem was solved. So first of all, in order to define the entanglement between two spins in a pure state, okay, you trace out 1 and this you compute the entropy, okay, or any other measurement. If the state is not pure, then you cannot use this this method. But you can define something which is called entanglement of formation. So you have the density, and you write this sum over I, pi, I, psi I. And this is a generic decomposition of the states A, B. And then you just define the entanglement contained in rho as the minimum over all possible decomposition of the density matrix rho in this form, and just take the minimum of this object with respect to all possible decomposition. This is called entanglement of formation. And this is essentially related to the fact that when you have two spins, or two qubits, you are just using Bell pairs as a quantifier of entanglement. Okay. So essentially you have, I'm going to say something which is not probably correct, but I will say, imagine that you have a certain number of Bell pairs, then by doing local transformation, you want to create M copies of the state, and essentially this ratio N pairs or N Bell with respect to M pairs is what entanglement is. So this is a complicated quantity to compute because you have to minimize overall possible decompositions. Now, a great result was obtained by Wouters, who showed that if you take this weird quantity, which is called concurrence, this is a monotonous function of this entanglement of formation. So you have to do that. So there is a recipe. So you just take the density matrix and then you compute this rho tilde from the density matrix. You find the eigenvalues of this object, rho times rho tilde, and the max between 0 and this the 4 eigenvalues gives you the entanglement. And this is something very easy to compute because essentially the whole minimization procedure has been performed. No, the minimization is simple, but the problem is that you have to find all possible ways to decompose the density matrix. So it's in general difficult in the sense that, yeah, so that's, while this is just computing a quantity. So basically he proved that this minimum corresponds to that quantity. What is this? Okay, so if you have a state psi AB, which is a pure state, the entanglement of a pure state can be obtained by you take the entanglement out of the entropy associated with the reduced density matrix rho A. Okay. If you have a mixed state, you cannot apply this. So you have to take all possible decomposition of the rho and then take the minimum. Okay. Okay, so I will go fast on this because I don't want to enough time. So you just take the entanglement between nearest neighbors, okay, between this point, this site, and this site. And there is a way to see that the system shows in the entanglement some critical behavior. But I don't want to spend time on this. I would like to describe the space dependence of the entanglement. So this is at the critical points. Okay. So at the critical point, correlations diverges. Yet, so spin-spin correlation will decay as a power law. Nevertheless, if you ask how entanglement between 2 points decays in space, it's highly short range. Okay. So entanglement in this form of site-site entanglement has no trace of the long-range correlations. So this means that if you want to look for universal properties related to the correlation length, probably you have to find a different partitions. So that's why I just want to give you this example. Or I will talk extensively about the block entropy, or you can do something else. And this is a work which was developed by essentially by the group of Sirac, Frank, Restrated, and led to the concept of localized entanglement. So you have the same problem as before. So you want to know the entanglement between these 2 points, the red circles. But now you don't ask the question of what is the entanglement in the ground state. You want to find out what is the maximum entanglement that you can just localize on these 2 sites, but just doing local rotations. So local rotations do not change the entanglement content of the system, but essentially they can swap entanglement around. So unitary rotation, but local, because yeah, unitary rotation. Yes. So in the first today, and yeah, I will talk about only unitary evolution. Okay. No, sorry, unitary, no, right, yeah, unitary, yeah, yes, you're right. Okay. So actually they show something very interesting, is that if you start with the ground state, as I told you before, entanglement is very, very short range, even when the system is in a critical point. However, the system has the possibility to localize entanglement over long range. Okay. So, okay, this is, I can say words. I mean, basically, they can show that localized entanglement can be localized with power law decay, gaining essentially the same long range features which are present in the ground state. So the message is that you can, when you are at the phase transition, at the quantum phase transition, entanglement itself can be, 2 sites entanglement can be uncorrelated with the critical behavior, but the fact that the system has a diverging correlation function means that the system has the power to swap entanglement around over large distances. And actually, they found, I think an even more spectacular result, that is, they found systems. I mean, I know the example of spin 1 Hamiltonian. So essentially, they took the AKLP model, which is a spin 1/2 model governed by this interaction, and they add local deformations. It is not really important what are these local deformations. They are not. It's not even important. I don't remember them, so don't ask, because this was my elegant way to say that I don't remember, and I forgot to write. However, what they found is that they had cases in which the Hamiltonian is gapped, so correlation length is finite, but in terms of this angle phi, they found that the entanglement length would diverge in places where the correlation length is finite. So this means that localized entanglement has transitions that are not present in the ground state of the system. So this psi E can be completely decoupled from the correlation length of the system. In order to get, let's say, a very nice view of the connection between correlation length in the ground state and entanglement, then we should have a look at the different partition. That is, just looking at the entanglement between two blocks of the system. And I will refer to this. I mean, so to these papers, especially the one by Pasquale Calabrese and John Carter. So since the overall system is pure, then it is enough to compute the entanglement entropy of the block. Then the result of Calabrese and Cardi show that there is very nice relations of the entanglement entropy with the correlation length. First of all, so a finite correlation length implies that entanglement entropy saturates. That is, essentially, it's a kind of area law, in the sense that the entanglement between these two blocks is essentially related to the boundaries. And in this case, a one-dimensional system, when it becomes critical, then we have a log deviation from the area law. Very important result was that the three-factor is universal for the system they consider, I mean, so related to the central charge. I will skip this because of time. The only thing, so I think my time is over. So I just last thing I would like to say is that, so this result tells you essentially that out of this huge Hilbert space of many body systems, the ground state occupy a very special corner. So they are not typical states. Okay. So the overall, so typically you would expect entropy to be volume-like, but the ground state is spatial. And here it's very easy to pick up the idea that basically if you have a finite correlation length, then you just cut a finite number of links, and then you end up with a way to see the entropy. So since, okay, so I stop here. Thank you. Okay. You have questions? Ah, okay, sorry, I did not understand. So it's local unitaries. No, I did not. If I said measurement, I was wrong. This one. Oh yes. So since if you do any local operation that is either unitary local rotation or just a measurement on a single site, entanglement cannot increase. Okay. Projection or any generic POVM measurements. So you are allowed to do anything that does not increase entanglement. Yes. So in the ground state, yes. So this is essentially the reason why MPS works so well in one dimension, because in one dimension it's area law or at most logarithmic increasing, and so the bond dimension of the matrix is under control. Okay, thank you.
So people and sign up for the dinner, please remember to put the name there. And apparently for the doctors, it's found other links. And then on the table.
So I don't know how to close it. Ah, no, but I don't know how to close it.
So land tickets are on the table
No.
here.